Okay, we're going to pick up here with chemical bonds, which is chapter 2. In chapter 2, it's the third section. So chapter 2.3. Now, the first thing we want to look at is covalent bonds. Now, as going through this, pay particular attention to these parts that you see in red. There's a good chance you're going to see those again come test time. So, covalent bonds. This is where we have atoms held together by sharing electrons. And the number of covalent bonds formed by an atom depends on how many electrons are in that outer shell, or what's called the valence shell. And so what will happen, unpaired valence electrons are going to be shared with other atoms so that they meet that octet rule. They have 8 electrons in the outer shell, or valence shell. Now it would be, instead of 8, it would be 2 electrons in the case of hydrogen and helium, since they only have the first shell. Okay, so let's look at some examples of this. So here's hydrogen, and notice the way it's written, one molecule of hydrogen gas consists of 2 hydrogen atoms bonded together. Okay, oxygen, one molecule of oxygen gas consists of 2 oxygen atoms bonded together, and so forth. So let's go to your textbook and look at these examples. So here's the hydrogen. This is on page 33 in the 9th edition. It'll be close to 33 in the 10th edition. Notice here's a hydrogen atom. Here's our 1 proton and 1 electron. That does not have a filled outer shell. So if the other atom that we have is another hydrogen, it has the same structure, only 1 electron in its outer shell, doesn't have a filled outer shell. These 2 atoms will move in close enough together that their outer shells overlap, and those electrons are in the outer shell of both atoms at the same time. Okay, so we can write this as H sub 2, or the other way we can show this is hydrogen. There's a straight line, another hydrogen. Now that straight line, that represents a one covalent bond, or 1 pair of shared electrons. Let's go down here and look at oxygen. So oxygen has an atomic number of 8, which means it has 8 protons. If it's electrically neutral, it has 8 electrons. 2 of those electrons will fit in the first shell. That leaves 6 electrons in the outer shell. It does not have a filled outer shell. So, if the other atom here is oxygen, it has the same structure. These can overlap. The outer shells will overlap, and they will share this pair of electrons, and that gets each atom up to 7. Still not enough, so it can share another pair of electrons, and that gets each atom up to 8 electrons in its outer shell. So 1 molecule of oxygen gas is 2 atoms of oxygen. We can write it as O sub 2, or we can show it as oxygen, and then these 2 straight lines, that's not an equal sign. Each straight line represents a covalent bond, or a pair of shared electrons. So 2 oxygen atoms held together by a pair of covalent bonds. Okay, now it doesn't always have to be. Let's go back over here for a second. Notice here's carbon dioxide, water, ammonia as examples of molecules where we have covalent bonds. So it doesn't always have to be 2 of the same atom bonded together to have a covalent bond. Covalent bond is just the case, here it is a case where we have atoms held together by sharing electrons as opposed to gaining or losing electrons. Okay, so let's go back to the textbook for a second, and let's flip over here, and let's see. Let me see here. Okay, here we go. Water down here. So water, here's your oxygen. It has 6 electrons in the outer shell. Here's a hydrogen with only 1 electron in the outer shell. Okay, that hydrogen needs another electron. So right here, The hydrogen will share an electron with the oxygen, so that puts 2 electrons in the outer shell of the hydrogen right here. And the oxygen, that gets it up to 7. So we can have another hydrogen share electrons with the oxygen, and right here you go, here's your other hydrogen. It now, by sharing electrons with the oxygen, it has 2 electrons in its outer shell, and the oxygen's in good shape. It now has a total of 8 electrons in its outer shell, and that gives us this water molecule. Okay, so oxygen and 2 hydrogens. Okay, now of course, let's go down here. Let's see if we can draw on this. Okay, so we could have, there's oxygen, and we show this with a straight line to a hydrogen right here, and then here's another straight line. That would be another single covalent bond to another hydrogen. So we have the water molecule. Okay, carbon dioxide, likewise covalent bonds, ammonia, covalent bonds. Let's go back over to the textbook for a second and see. Well, I said we're going back to the textbook. I have to turn this off. There. Okay. Let's see. See if there's anything else to look at here. That's going into ionic bonds. Okay, so let's go back here. Okay, so now then we have polar and non-polar covalent bonds, and we've got this term electronegativity. So electronegativity, this is a measure of an atom's attraction for electrons, and down here we've got some electronegativity values. I'm not going to ask you anything about these numbers on the test, but just notice right here, oxygen has a much higher value, a much stronger pull for electrons than hydrogen. So if we go back here to our previous, well, my drawing's gone now. Okay, so let's just go on down here. So let's look at nonpolar covalent bonds. Atoms have the same, this is where atoms have the same or similar electronegativity, and the electrons are shared equally. There's no charge on the molecule. So notice right here, if we have two of the same atoms of the same element on either end of that covalent bond. So for example, right here, there's hydrogen. Okay, here's a covalent bond. Here's another hydrogen. Okay, they're both hydrogens. They both have the same pull for electrons. So these electrons are going to be evenly shared between the two atoms. Same thing with oxygen. Okay, so oxygen, I know that's not a very good O, but there's our oxygen, 2 covalent bonds, another oxygen. We've got the same element on either end of those covalent bonds, so they have the same pull for electrons. Those electrons are evenly shared. So this molecule does not have a charge on it. Now in some cases, rather than being the same atom on each end, or the same element on each end of the covalent bond, we have elements that don't have a large difference in their pull for electrons, and then we have the fact that the molecule is symmetrical, which makes it nonpolar, which makes it non-charged. Okay, so let's see, let's erase that and go on down here. Okay, turn that off, I guess. Okay, so nonpolar covalent bonds. So right here, there's an example of methane molecule from your textbook, and you notice it is symmetrical, and so it is nonpolar. We're going to concentrate, as far as testing purposes, we're going to concentrate on these right here, which is sort of the extreme example. If you have the same element on either end of that covalent bond, those atoms have the same pull for electrons. The electrons have to be equally shared. That is going to be a nonpolar covalent bond. Okay, let's look at polar covalent bonds. Polar covalent bond, the atoms have different electronegativities. They have different pulls for electrons. So the electrons are unequally shared between the atoms within the, that's supposed to say molecule, and this molecule has weak charge on each end. So for example, if we have an oxygen and a hydrogen, this oxygen has a much stronger pull for electrons, and the electrons are skewed down here towards the oxygen end, and that puts a slight negative charge on this end, slight positive charge on this end. So let's go look at this slide. And so here's our water molecule, and the shared electrons spend most of their time up here around the oxygen. Plus the fact that this being hydrogen, it just leaves these bare positive charges sticking out down here on the hydrogen end of the water molecule, and so that gives us a weak negative charge up here on the oxygen end and a weak positive charge down here on the hydrogen end. So this is a polar covalent bond where we have electrical charges. Okay, so let's go on down and look at ions and ionic bonds. Now an ion, tell you what, let's stop this one right here, and we'll pick up with ions and ionic bonds in another YouTube. Okay.